Hello, let's do number 12, standing waves in an air column. We've just done standing waves in a string or wire, and we're going to see that we can get standing waves in an air column. Remembering that the standing waves in a string, they were examples of transverse waves, whereas these guys, because they're dealing with sound, they're going to be longitudinal waves. And we have a slightly different pattern, and we have two choices as well. In terms of an air column, we can have a closed air column or a column that's open at both ends. This one, here's our speaker or the source of the sound. So it's open at one end, closed at one end, or open at both ends. And this is what we're trying to represent here is the actual standing wave. And so when they draw this symbol or wave like this, it means that is a node. And I've lost my pens, I'll just try and get them back. There they are. So if we write on this right now, we should, so that's going to be a node there, that's a node there. And the thing about air columns is that we always have to have an antinode at the source end or the open end. And so any end that's open has to be an antinode. And so what they're trying to show here and here is that the particles can move the maximum amount from their mean position. And so that's going to be an antinode. So we'll have a node there and we'll have a node there. So we've done our labeling. What does it mean? Well, this is our fundamental frequency. And so at this frequency we get the most basic resonance, which is to have a node here and an antinode there, nothing in between. And in this case the length of the wave, because this represents, if this is a center line, drawing that down there like that, let's just fill that in a bit more better. Okay, this is just a quarter of the actual whole wavelength of the standing wave. And if we move along, and so here the wavelength is 4L, here the wavelength is 4/3. How do we get that? Well, let's draw in the wavelength. We go up here, down here, and then it's got to come back up to there. So that's going to be a quarter, and then we have a quarter and a quarter, quarter there, quarter there, quarter there, quarter there. Is that right? So that's the whole wavelength, but that represents a third, you see, of the length. Okay, and so therefore we're actually got, if that's a quarter of the wavelength, it's a third of the length of the pipe. And so we've got 1, 2, 3, 4 thirds, and there's our 4/3 length of the wavelength. Let's get rid of that. Okay, now, and we'll go through our next slide, we'll show you a progression of these. Now, with it being open at both ends, we have a similar arrangement in that this, hopefully you would recognize that this represents half the wavelength, and therefore the whole wavelength is 2 times L. Now, we don't have to have a source at this end. What happens is that the wave bounces back, it comes to the edge here, and because there's a change of medium going from air in a tube to air out in the open, we get the wave bounces back and there's a phase change. Is there a phase change? Yeah. And then so this acts, and that's why we can have a standing wave here, because it acts like a boundary, whereas here it just bounces off the back of the end. I think the next slide's a little bit better. This is better. So this is trying to, I forgot to mention, what sort of situations do we get standing waves in pipes? Well, pipes at open ends are things like a flute or a organ pipe, all the musical instruments, clarinets, siren, like whistles that you blow on, Have you ever blown onto the top of a bottle and got a resonance, like a loud note? They're all examples of standing waves in pipes, and some are open at both ends and some are closed at one end. Now here we go. This is just trying to get you around the nomenclature. And so back with the vibrating strings, we had a fundamental, which was the first harmonic, and then each resonance after that. So these are our frequencies that we get, and in between these frequencies you just get chaotic interference. And so the next resonance is called the second harmonic, which is this guy. So here, this is open at both ends, so you must have an antinode at both ends, and you have a node between the antinodes. So what you do to find the next one is you put in, slip in an antinode, and that gives you your two nodes. And then the third harmonic and the fourth harmonic. And as with vibrating strings, we have the overtones, and the overtones are the numbered resonances after the fundamental. So that's the first overtone, second overtone, and third overtone. Alright, and you don't have to remember all these formulas, but you do need to understand how to draw these guys and how to name them. Now here we've got it closed at one end, so you must have a node at the closed end, must have an antinode at the open end, and the consequence of this is, if that's our fundamental or our first harmonic, because we've now introduced a node here, and we've got two antinodes, we would call this the third harmonic. We're actually missing what we miss all the even harmonics because they can't form. And so the next one is the fifth harmonic, and then you have the seventh harmonic. Now in terms of the overtones, however, because they're just named numbering of the resonances after the fundamental, we still have our first overtone, second overtone, and third overtone. So there's a little clash of numbering there that sometimes throws students. Now this one is out of your textbook. It's trying to represent something like a flute or a clarinet, and it's closed at one end. So there's our first harmonic. This is the third harmonic or first overtone. There's all our equations, and then open at both ends, you get all the resonances as well. Now on the OneNote there'll be some videos on what's called a Rubens tube, and what a Rubens tube is imagine you had a pipe like this, and you pumped in a flammable gas, and what you had is a whole series of holes, and what you do is you light the series of holes, much like a burner on a barbecue, and the gas is alight up here, and then you introduce a sound into the tube that's got the unburnt gas in underneath it. And what happens is, as you change the frequency, you get variations in pressure within the tube, and those variations in pressure correspond to the variation if you have a resonance. So let's say you had, if this was the resonance, let's go to red, okay, and you had all your tubes here, what you would find, this would be high pressure, this would be low pressure, and so all the flames that are coming out would be small there, and then they'd be bigger there. I'm trying to draw this, and then you get bigger flames depending on how high the pressure is. Okay, and because there's a standing wave within the tube, you get this distribution of flames, and so you can actually see the standing wave within the tube, the gas tube. And then what they do is they play music through the speaker, and it varies the tune, and you can see the resonances as they appear, and then you can also see the chaotic interference that's happening, and so the flames are all over the place. So have a look at that, it's pretty interesting. I think so anyway. And then we've done that, and we've done that, and then we'll do a prac that actually reinforces this, hopefully. Now on the OneNote there's a whole lot of videos that relate to waves. There's things called rogue waves, which every now and again you hear about boats being capsized because of rogue waves. They're out in the ocean, it might be a bit rough, and then all of a sudden this huge wave comes. And so we'll just talk a little bit about Deadliest Catch, I think that one is, so have a look at that. Waves in space, you think there's no medium in space to carry mechanical waves such as sound or anything, but there are waves in space, and so there's a video on that. If you remember back when we were talking about having these big wave generating power from waves, and one of the techniques was to have a long, like a snaky thing on the surface and it moving. There's a video about that, how that works, and there's a video on wave power, and there's also the Japanese whaling fleet video, which you may have already watched, but they'll all be on the OneNote. And the next video, which will be our last one, will be about hearing. Alright, see you later.